Welcome students. Welcome to today's lecture. Today we are going to discuss the pneumatic conveying. Okay. What do you mean by pneumatic conveying? So pneumatic means basically it is air. Okay. So conveying means transport. So with the help of air, we're going to transport solids. That is basically pneumatic conveying. Okay. So what do you mean by pneumatic conveying? The transport of particular materials by air or other gases. Okay, so you are basically using gases to transport some solids. Okay, so basically we can say the flow of gas solid natures. Okay, so in pneumatic conveying, basically the particle size range we use is from 20 micrometer to 50 millimeter. Okay. So, but you cannot use finer particles or particles lesser than this size, because if you have finer particles, they will stick together, form agglomerates or to the walls of the pipe, right? So basically, suppose you want to transport, let's say, some sticky material like atta. So atta, the size particle is very small, right? So it will come in between this. But the problem is they stick together. They will stick to the wall of the pipe. Okay, and it will create problems, like it will block the pipe. Okay, so very fine particles create some problems in pneumatic conveying. Okay, so in pneumatic conveying, we have basically three modes of transport. So first we have dilute phase transport or lean phase. So what do you mean by dilute phase transport? So dilute phase means you have air, right? Air is, let's say, air. You want to transfer solid particles, and the volume fraction of solid particles is around 0.005. So you can see 0.005 means 5%. So if you take this volume, 5% of the volume is occupied by the solids and 95% is occupied by the air. That means it is very dilute phase. Very small fraction of particles is moving, right? So it is called dilute phase transport. When you transport solids and their volume fraction in the suspension is like less than 5%, then it is called dilute phase transport. And next we have moving bed. So you can see moving bed. So it must be very dense. The volume fraction of solid particles will be very high. So let's say some kind of particles have collected over here, air passes through this side, so this whole bed will move, right? So this kind of transport will be called moving bed transport. As you can see, the volume fraction of solid particle is 0.6. That means 40% of this transport will be air, 40%, and 60% of the volume will be occupied by the solids. So as you can see, it will be very dense. Okay. And third, we have dense phase transport, right? So in dense phase transport, the volume fraction of the solids is 50% or 0.5. So it is lesser than the moving bed. So in dilute phase transport also, we will have very large volume fraction of solids. Okay, we have air. So it will also move as slug. Okay, this is called slug. This all solids are stick together to form a slug. They almost block the pipe. So this kind of transport are called dense phase transport. Okay. So in dense phase transport, there is very risk of blockage, right? So if this pipe is blocked, then there will be no flow of solids and the pipe can break. Okay. So in within pneumatic conveying, right, transport by gases, we have two kind of transport: horizontal transport and vertical transport. vertical transport and horizontal. As the name suggests, suppose you have a pipe, it is in horizontal position, so and you are transporting solids, right, with the help of air. Right? This is horizontal transport. What about vertical? Just the pipe is in a vertical direction. So now you have solids and you're putting air from the bottom. So this is vertical transport. So first we'll take care of the horizontal transport. So in horizontal transport, suppose this is air, the air is flowing with some velocity and we have solid, right? Suppose this air is at very high velocity, so all the particles will flow with the air, right? But if you reduce the air's velocity, then what will happen? The velocity of the solid particles will also reduce. So if you reduce the velocity of air, then you can observe certain patterns called flow patterns, right? So what are those? So let's discuss one by one. So first one is uniform suspended flow. So as you can say, uniform particles are there. So we're discussing horizontal transport. So uniform suspended, all the particles are suspended in air and it is distributed uniformly. Okay. So they will flow uniformly. So that is uniform suspended flow. Non-uniform suspended flow. This is like non-uniform. So it's kind of uniform, but it is non-uniform in the sense the heavier particles will be settled because of their higher gravitational pull. It will be at the bottom. So smaller particles will be suspended at the top and heavier particles will be at the bottom. Okay, so it is non-uniform suspended flow. Then we have slug flow. So what is slug flow? So what is happening in here? So they will form some slugs. We'll have above it, it will be, so these particles are deposited here. But this slug will move with the air, right? So as the air is flowing, it will apply some drag force on this slug, so it will also move. So this slug is moving. Okay. So what about dune flow? In dune flow, it is same as slug flow. Only the problem is this will not move. We are talking about dune flow. This slug will not move now. Only the particles above it will move. This dune, it's like sand dune. So the dune will not move. Okay, this is called dune flow. Only the particles above the dune will flow. What a moving bed? So what happens is the particles is like your air is flowing. This is the feed point, right? Your solid particles are entering here. So at the feed point, we have a very continuous, solid bed. So all the solid beds are forming kind of bed at the feed point. Okay, and this bed will develop. So along the flow directions. Okay, so this bed. So this bed will also move. That's why it is called moving bed. So this kind of flow pattern is called moving bed. Okay. Stationary bed. Now the bed will not move. Okay, these solid particles have deposited at the bottom. Only this space is empty, so solids can flow in this direction. The bed will not move. That's why it's called stationary bed. Only above the bed the solid particles will move. Okay, now lastly the plug flow. Now if all the particles get deposited and it will cover all the pipe, cross-sectional area of the pipe, then it is called plug flow. So it can sometimes block the pipe also. Okay, these 7 types of flow patterns is observed in horizontal transport. Now, suspension mechanism. So during the horizontal transport, how the main aim is the air is flowing and we have solid. So if the solid particle wants to move, then it should be suspended in air, right? Then only it will be easily move. If it gets deposited at the bottom, then it will not move. So main thing is the solid particles suspended in air. So how they are suspended in air? So we're talking about how they can be suspended in the air, or they are suspended because of some mechanisms, right? So first one is we have aerofoil effect. Okay, so while studying the drag forces, we did this, right? We calculated drag force. So suppose the solid particle is at an angle. This is projected area, and fluid is coming like this, right? So we'll have two component of drag force, right? One in x direction and one in y direction. Okay. So this y component of this drag force will be lift component. So because of this y component of the drag force, right, the particle will be, because we are talking about horizontal transfer, so the particle will be lifted upwards, so it will remain suspended. And next one is Magnus principle. Right? You already know Magnus effect, how the footballer swings the ball, and right, because of the Magnus effect. So what happens if the particle is rotating, right, in this pipe? So during the flow, let's say particle is rotating. So as you can see, the air direction is in this direction, right? Air. This particle is rotating like this, clockwise. So what happens at the top of the ball, of the particle, right? The air and the particle is moving in the same direction. But at the bottom, the air is in this direction, but the particle is rotating in this direction. So what will happen? There will be, less, heavy, great pressure force here. Okay. So pressure will be high at bottom, and there will be low pressure here. Because the air is moving so fast, so there is, at any instant of time, there will be, the pressure will be less. The air will be less in that particular point. There will be no air at that point. While here, the particle is rotating in this direction, and air is coming in this direction. So there will relatively, the air will be there. It is not moving very fast. So there will be higher pressure at the bottom than the above the particle. So, and there will be, air will move from high pressure to low pressure, creating a lift on the particle. This is also the way how the particles get suspended in air while during the transport. Okay. So as I told you, we have three kinds of pneumatic transport: dilute phase transport or dilute phase conveying. The second one was moving bed conveying. The last was the dense phase conveying or dense phase transport. So this is straightforward, how much energy is required, right? So you can see, so if you have larger volume fraction of the solids, you will require higher pressure drop or higher energy, right? So you can read this. Next, how to determine the solid velocity of the particle. So during horizontal transport, you have air is flowing at some velocity. So how will you determine the velocity of this solid particle? So we have certain correlations called correlations, because these equations are obtained by doing experiments by some scientists. Okay. So okay, we will come to this point later. So those correlations. So this this table gives you the physical properties of solid used for pneumatic conveying. So coal A, it is the shape is rounded and the particle size is around 1.5, right? So and dust particle. So mean particle size is like 0.75 mm. Density is 1400 kg per meter cube, and terminal velocity, or you can say free falling velocity, is 2.80 meter per second. So this is the correlation to predict the solid particle velocity. So US is the particle velocity, so or solid velocity, and UZ is the gas velocity. So this is gas. So what is the velocity of gas? So this is UZ. It will be given, and US is the solid velocity. You can predict it using this equation. And what is U naught? So this is the terminal velocity. Okay. Suppose you take coal A, then you have to take the terminal velocity 2.80 meter per second. You can put it here. Again here. And what is rho s? This is the density of the solid. Okay. Also, what is slip velocity? Slip velocity is nothing but kind of relative velocity, UR. So it is nothing but difference between the gas velocity and the solid velocity, UG minus US. Now, this correlation predicts the pressure drop required in the x direction. So this equation is for 25 mm pipe. Okay. So you can see this is a pressure drop in x direction, and this is a pressure drop of air. This is the solid velocity. This is the feed rate, that is kg per second, and U naught is the terminal velocity. Okay, so if you plot this versus this, then you should get a straight line, right, of slope 2805. So you can see this plot. This is given in 51.19. So the plot is here. So if you plot this with versus this, you will get a straight line. So you can predict the pressure drops for solids. Okay. So like say coal C. So you want to predict the pressure drop for coal C. What is the terminal velocity? U naught. Right. So you can find it. So just draw a vertical line. You will get the pressure drop required. Okay. Now, so this is pressure in horizontal 25 mm conveying line. So this is your pipe, horizontal pipe, and your air is flowing because of the pressure drop, right? And this is your feed point, right? This is feed point. So how the pressure drop changes along this line? Okay. So distance from the feed point 5 meters. So let's say up to this. So this is a distance from the feed point, right? So total distance is 5 meters. So you want to see how the pressure changes along the direction. So at feed point, it will have the maximum pressure. Okay. So we are calculating this pressure drop for the air and solid mixture first. So as you can see, the pressure is decreasing along the line, along the distance from the feed point. Okay. So it is 0 at this point. Okay. And for clean air means there is no solid, so it is also decreasing like this. Okay. So why this is important? Because while calculating the solid velocity, you cannot calculate the solid velocity in this region. Okay, don't calculate in this region or from the feed point. After this only you have to calculate the solid velocity. Okay, because after this point only we'll have, constant solid velocity. In this region, the solid velocity will not be constant. And let's see how the pressure drop varies with the feed rate, okay, and air velocity. So on the x-axis we have air velocity. Right? On the y-axis we have pressure drop, millimeter of water. It's basically using a manometer. Okay, so and we have different lines. So first line is this one, clean air. So there is no flux, right? There is no solid. So flux rate of solid is 0. So clean air. So this is how pressure drop varies with the air velocity. So if you increase the air velocity, then pressure drop will also increase. Okay. Next we have the flux rate, solid flux rate of 0.009. So it will increase like this. Again for this, like this. Right? So with increasing solid flux, the pressure drop also increases, right? At constant air velocity. Also, you can see for all the curves, they go through same like this. First, they decrease, go through a minimum, then again increase. Okay? This is a typical pattern. So you can predict the solid velocity using this, and with the help of this table. Also, you can predict the pressure drop. Okay, delta px. You can use this equation if your pipe diameter is given. So this is the pressure drop variation with respect to the diameter. Okay, earlier in this equation there is the diameter was fixed 25 mm. Okay, so we don't have diameter variation here, but if you want to calculate the pressure drop for different diameters, so you can use this equation, because this d is the diameter of the pipe. Okay, so the dense phase conveying, as we already discussed, for dense phase we have volume fraction of solids 0.5, almost move as a slug, chunks of solids together. Okay, or maybe like complete block. So for dense phase conveying, it is very difficult to predict. Okay, so there is not very established equations to predict the pressure drop. Okay, you have to do the experimental for each problem separately to calculate the pressure drop and the solid velocity. This was the graph of earlier, that pressure drop versus diameter variation. As a vertical transport. Okay, so now instead of using horizontal pipe, we are using vertical pipe, and air is moving at the bottom, and solid will also fed here. Okay. And you have to transport solids in vertical transport. So this is similar to as fluidization. Okay, so if you know minimum fluidization velocity, so what is the minimum fluidization velocity? Suppose we have solids here and air is entering at certain flow rate or at velocity. So what will happen as you increase the air velocity, this bed, this is a solid bed, it is fixed now, the position is fixed. As you increase the pressure drop or the air velocity, what will happen? These particles start to move, right? At that point, when the terminal velocity of the particle will be equal to the drag force, or just the particle will start to move, okay, with air, that is called minimum fluidization velocity of particles. Okay, so the particles will only move with the air if the velocity of the particles is greater than the terminal velocity of the particles. Okay, So the pressure variation along the length, this direction, is given something as this. So delta P by delta L minus and equal to 1 minus Eg. This is the void fraction. Void fraction is empty spaces by total volume. Empty volume, I mean the voids, volume of the voids divided by total volume. Rho is the density of solid, G is the gravity. Okay. So why this pressure gradient is negative? Because at this point we have higher pressure. That's why the air is moving. And here we have low pressure. So if you take the change in pressure, so this minus this. So to make it positive, it is given minus. Okay. So next we'll discuss the hydraulic conveying. So this was pneumatic conveying, means transport using air or other gas. In hydraulic conveying, we'll use water instead of air. Okay. Thank you.